For being a good sport. The real title of the talk is Statistics meets Computation, Fast Global Convergence and High Dimensions.
Okay, so thanks to the organizers for putting together a great workshop. I guess I don't know how I feel about acknowledging my students after that. Just joined work with Al Agro and Megaban. So Han's not here, so he gets acknowledgement. Okay, so I'm going to be talking about a class of problems that sort of popped up in many of the preceding talks. So I'll be general first, and then I'll work through some particular examples. Right, but there's many problems in which you want to estimate some unknown parameter. This could be a sparse vector, it could be a low-rank matrix, it could be a sum of a low-rank matrix and a sparse matrix. And many of our methods are based on solving optimization problems. Right, so we have a loss function that depends on data. We have some number n of samples, and often we have some kind of regularizer that tries to encourage some kind of low-dimensional structure. So like Ma said, we're really seeing an explosion of data, and we need things to enforce structure. So what I'd like to talk in this, go through in this talk is interplay between things that statisticians or learning theorists are interested in. Right? So what they're interested in is when you solve this problem using some method, you get some estimate. You get an estimate of a sparse vector, you get an estimate of a low-rank matrix. And they'd like to know how close is that estimate to some unknown truth in the world. Right? So that's one kind of error we'll call statistical error that they'd like to bound. On the other hand, optimization theorists, what do? Well, they have some algorithm, some particular algorithm, hopefully it's efficient. That algorithm generates a sequence of estimates, it's called in theta t. And what they'd like to understand is how quickly does the optimization error drop as a function of t. So these often are studied separately, but what we'd like to do is sort of understand some interplay between these two things. Okay, so the algorithm, I'll study one algorithm. It's a simple algorithm, but it takes different forms for different problems. It's an old algorithm, it's not a new algorithm. I think some of the ideas I talk about will apply to other algorithms, but let's fix on this one. So just projected gradient descent. You have some constraint set. Projected gradient descent says, we're assuming this is differentiable. It says take the derivative, start somewhere, walk in the negative gradient direction. If you walk outside the set, then you project back on. Right? So it's a simple algorithm. We'll see that it takes the form of soft thresholding or singular value thresholding in particular cases. Now, what we'd like to understand is, at least classically, it's very well understood how this algorithm behaves. This is old work, for instance, due to Nesterov and others. If you have convex problems that are just convex, you have no smoothness conditions, I'll explain what that means in a minute, it will converge, but you'll get relatively slow rates. You'll get sublinear rates. What's more interesting to us here is if you have stronger conditions like strong convexity and smoothness, you'll get much faster rates. And what we're interested in is in these fast rates. Okay, so just to give you a picture, right, if you plot iteration number versus log of the optimization error, if an algorithm is converging sublinearly, it means the error is dropping off like 1 over t or some polynomial like that. So if you take logs, then you'll see a fairly slow decay. What it means, obviously, if you have linear convergence, it means it contracts by a constant factor every iteration, so you'll get a linear rate of convergence. You'll go on. Right? So what happens in practice when you apply this kind of algorithm to standard problems? So what's one standard problem? One standard problem is sparse regression, right? Where you have a regression problem, you have a sparse regression vector that you're trying to estimate, supported on a sparse subset. An estimator that many people study is you minimize a quadratic loss subject to an L1 constraint. So that's a particular case of the estimators I mentioned. And projected gradient's very nice. You take a gradient step. Projecting onto the L1 ball is essentially a soft thresholding operation. So that can be done quite efficiently. Now, where this algorithm is interesting, and all of this talk is focused on, is high dimensions. High dimensions just means that the number of samples n is much less than the ambient dimension d. Right? So there's many problems where n might be 100 and d could be 10,000. So you want to understand what happens when this matrix is rectangular in this way. Okay, so if you apply this algorithm with a constant step size, you apply it for different sizes of problems, 5,000 dimensional, 10,000, or 20,000, Again, plotting iteration versus log optimization error. What you see in all cases are straight lines, roughly. Maybe even slightly faster than a straight line. And here we're using 2,500 samples. So these are very underdetermined problems. Right? So it's behaving as if the problem were strongly convex. It's converging quite fast. But these problems are not strongly convex. There's no way they can be. Because if n is 2,500 and you're working in a 10,000 dimensional space, this, the Hessian of this function is rank degenerate. Okay, so we'd like to explain that. There's been past theory on these kinds of problems, but it doesn't really explain this phenomenon. So many people have looked at Nesterov methods or gradient methods and have shown they will converge sublinearly. That's not what's happening here. It's much faster than sublinear. Various people have imposed certain kinds of global smoothness conditions. Roughly that means that the gradient of the loss function is Lipschitz continuous. That doesn't hold for these problems. For high-dimensional problems, you don't have global smoothness. So again, these kinds of results don't guarantee. Other people have looked at particular cases where you have a sparse regression with a restricted isometry property, and they proved some nice results. This problem here does not satisfy the restricted isometry property, so those results don't explain what's happening either. This is a fairly poorly conditioned matrix in some ways, so it certainly isn't close to an identity in any sense. So what we'd like to do is, we'd like to have some general theory that would explain that. We'd also like to explain low-rank matrix problems. We heard in this session many nice talks. Heard a couple talks that involve matrix completion. Right? So I'll be quick here. Many of you know this, that what you're trying to do is you have a very large matrix with, let's say, individuals and items. It could be movies, or for Amazon it could be things like books or other such things, CDs. And what happens is you observe, in general, you should probably assume you observe noisy ratings. People don't rate things in a noiseless way. But you have a lot of missing data, so it's a very under-constrained problem. I think this was first formulated as a kind of low-rank problem by Nadi Schrebro and his co-authors about 7 years ago. Okay, so what's an estimator for this? Well, a standard one we've heard is the nuclear norm is a good surrogate for rank. Again, you can do the same thing. You could do the quadratic loss subject to a bound on the nuclear norm. And many people have studied this kind of estimator for noisy low-rank matrices. Projected gradient descent is, again, reasonable. It's soft threshold of singular values. You could debate whether it's expensive to compute singular values. We heard some nice talks about how that might be sped up, but certainly it's not an unreasonable thing to do. And what happens when you do this in practice, again with constant step size? Well, here it's more interesting. So this is a matrix with 40,000 entries. And what you see is that the convergence rates are actually, convergence, non-convergence is actually sample size dependent. If you have a very large sample size, this number is, what we do is generate roughly 25 times the rank of the matrix times the dimension, not d squared, so dimension is 200. So here you have more observations, here you have 25 times less observations. So larger sample sizes, you get nice linear convergence. If you undersample too much, you don't actually converge, you oscillate. Right? So there's something interesting, some sort of interesting phenomenon that has to be predicted here, and it's going to be a sample size dependent phenomenon.
So what's the size of the matrix? What are these? You had an n by d before, or d by n.
Right, so here, D is, it's a square matrix, it's 200 by 200.
Okay, so not the field, it's a square.
It's a square matrix, so we're trying to do low-rank matrix recovery here.
And that's the matrix.
Right, so in terms of this picture, I'm saying that it's a matrix that's 200 by 200, and n is the number of observed entries. Right, so you want n to be less, certainly much less than d1, d2, or d squared in my case. And what we're saying is n is roughly the rank times, let's say, the longest side length. I was looking at square ones there.
The rank is 200, or you just do some threshold?
In that example, probably we've studied many different cases. So q equals 0 means it was exactly low rank. You can do it for approximately low rank. I don't remember offhand what it was. It was maybe 10. This is a low rank matrix. Netflix people say it might be rank 4 or something like that, so it's reasonable. Okay, so let me give you one last example, and then I'll sort of try and give you the high-level story. I won't go into this in detail because it's actually work that one of my students, Pauline, presented at the main workshop here. But essentially, when you have a missing data problem, it often leads to non-convexity. And what we'll see is the theory I'll present actually has implications for non-convex objective functions as well. So if you take a non-convex objective, it's non-convex in the right way, it's an objective that Pauline constructed for missing data, and again you plot the convergence rate of projected gradient descent on a non-convex problem, you again see over multiple runs, you see a linear rate of convergence. Right? So that's an interesting phenomenon. It's a case where you have a non-convex problem, but the consequences of what I'll present next is actually in certain cases you can guarantee that for non-convex problems you can solve them up to a fairly small error. We're going to see when we're going to solve them up to something that's smaller than the statistical error problem. Okay, so those are some examples. Let me just introduce a property of estimators. It's something to do with loss functions and something to do with regularizers. And then I'll flesh out some consequences of it in optimization and look at some specific models. Okay, so if you want to prove that an objective function is strongly convex, what you want to do is show that it's lower bounded by a quadratic form, right? That it has curvature in every direction of the space. Now, you can't do that when your sample size is less than the ambient dimension of the space. Because if you looked at the Taylor series expansion of your loss function around the truth, if you perturb it a little bit in some direction delta, there are going to be some directions that are good. A good direction is a direction like this where you do have curvature, but there are going to be many, many directions, a whole subspace where you see nothing, where the loss is completely flat. Right? So somehow those are very bad directions. You can't expect to do anything. You can't expect an optimization algorithm to converge geometrically or linearly if it ever encounters these bad areas here. Right? So what you have in all of these problems is you have a notion of how the regularizer might help you. Right? So what you say is, we're going to look again at the Taylor series expansion. We're going to look at the error in that. And we're going to ask that that's lower bounded by something quadratic, but we give you a little bit of wiggle room. Right? We give you something that's proportional to the regularizer squared. So if this term were 0, then that's just ordinary strong convexity. But this definition it's interesting because we allow you a negative slop there. Right? So what it's saying is that as long as your optimization algorithm walks in directions where the regularizer of the direction is quite small relative to something like the L2 norm or the Frobenius norm, then you're going to have curvature, you're going to have good behavior. And so the name of the game is you'd like to be able to show that an algorithm, and we will show the projected gradient descent, we're going to show that we can make it walk in exactly a space where this term is dominated by that. So I just said that. There's also an analogous definition. If you flip the inequality sign, you have a notion of smoothness. Okay, so that looks like a weird definition, but it holds for many problems. If you just look at least squares problems, then it's actually equivalent to what's known as a restricted eigenvalue condition. These are conditions, I think, first proposed by Bickel et al. They're much weaker than restricted isometry conditions. They're related. They're controlling eigenvalues of your design matrix in a regression problem, but they're much weaker. So there's no sense that you have to be close to an isometry. They hold for low-rank matrices in nuclear norm. You can again prove with high probability that something like this holds. They hold for not just quadratic losses, they hold for generalized linear models, things like exponential losses or Poisson losses or logistic loss. So there's a fairly broad class of problems for which these kinds of properties hold. Okay, now we need one more ingredient. Skip that slide. So what we have so far is we have a sort of condition on the loss function, and it needs to interact with the regularizer in a certain way. And now we need another condition on the regularizer that sort of says that it penalizes bad deviations as much as it can. So Yima alluded to sort of a more general viewpoint on many kinds of regularizers. Here's one. There's others in the literature, but I think this is a useful one in some ways. We say that a regularizer is decomposable if you can find a subspace, and that subspace is typically where you want your parameter to lie. It could be a subspace of sparse vectors. It could be a subspace of low-rank matrices. It could be a subspace of sparse functions if you're doing non-parametric problems. Right? So what we want to have happen is that we'd like you to be living in the blue subspace, and we're worried about deviations in the red part, in the orthogonal complement. And you say that a regularizer decomposes if whenever you take something good, so alpha in the blue subspace, and you add to it something bad in the red subspace, then the regularizer splits. It splits into two terms. Right? So one way of thinking about this is what I give my students. It's called tough love. Triangle inequality says that this is upper bounded by the sum. And so what this is saying is that this regularizer is going to hurt you as much as it possibly can if you ever move in a bad direction. Right? So there's a sense that it's trying to enforce the structure that you're after, whether sparse vectors or low-rank matrices. It's doing that as strongly as possible. Right? This holds for many things. It holds for L1, it holds for weighted L1, it holds for group sparse norms, it holds for nuclear norms, it holds for sums of decomposable norms. So for robust PCA, if you take nuclear plus sparse, again, this holds. Right? So it's a fairly general class of norms that satisfy this if you choose these two subspaces in the right way. Okay, so here's the main result. What you should take away from the previous is that we're looking at loss functions that satisfy a restricted notion of strong convexity and smoothness. We're looking at regularizers that satisfy this decomposable property. Those are the two conditions. And the main theorem is the following, that if you have a decomposable regularizer, then what we'll guarantee is we'll give you a contraction factor, something between 0 and 1, and we'll give you a certain tolerance, a certain amount of error, such that the optimization error decreases geometrically with that contraction factor. Right, so this first term, kappa is, let's say, a half. That's vanishing quickly. It's like 0.5 to the 1, 2, 3. It's exponentially decaying. But we're not going to quite get all the way to the optimum. We're going to get to the optimum plus a little bit of error here. And this error depends on essentially the size of the two subspaces. We can make this precise for various models. Right? That's a deterministic statement. There's no probability in this right now. Where the probability would come in is if you had a typical, some kind of learning setup, you'd have to verify that those conditions hold. Okay, so I think the picture is easiest. What this is saying is if we look at optimization error, so the first error and the first error, the second and the third, it's saying that it sort of follows some decreasing path. It's contracting geometrically. That's where we'd like to get to, right? That's the anoptimal solution of the full problem. The solution doesn't have to be unique, actually. And what we're guaranteeing is that very quickly you'll get to a certain radius epsilon of the optimum. Right? So this is going to be an interesting result as long as we can say that that epsilon is relatively small. Right? And because we're doing learning, we have a very precise notion of how small we want that epsilon to be. We don't really care about the optimization problem. Right? We only care about getting theta hat as an estimate of some underlying truth. Right? So the point is what we're actually after is the unknown parameter theta star. So as long as I can guarantee that this error, this epsilon in our optimization is smaller than the sort of statistical error in estimating the parameter, whether it's a vector or a matrix, then this is a useful result. And essentially under many cases what we can show is that what you'll get is geometric convergence quickly to a radius that's little o of the typical statistical error in your problem. Right? So I think that's an interesting sort of thing to take away, because if you're an optimization theorist, you might say, oh, what are you doing? You're only giving me some, you're not actually solving the problem, you're only solving it up to some tolerance. But if you're in learning, then this is exactly the kind of result you want, because you didn't care about the optimization problem to start. What you cared about was the thing you were trying to estimate. So there's a sense that this result is saying, well, you don't have to over-optimize. There's no point to optimizing beyond sort of the inherent noise in a learning problem. Okay, so How much time?
10.
10 minutes, okay. So this is a general result, but in the remainder, let me just sort of unpack it in one particular case. You can do it for many problems. You can do it for matrix completion. You can do it for matrix decomposition or robust PCA. But let me unpack it in the sort of easiest case, which is sparse regression. If I do that, you'll get sort of a sense, a more precise sense of what these terms mean. Okay, so if we do sparse regression, I'm going to do it with a random design. So it means what you're going to be observing are xi's that are random. They're not from the identity distribution. They're not random projections. They might have a very ill-conditioned matrix sigma, but you're giving standard sort of linear observations. And we're going to solve, we could solve the lasso with a quadratic loss, or we can do it generally with any kind of log linear loss. So this would include logistic regression or exponential Poisson regression, things like that. Now, what our theorem says in this case, it says that if the truth belongs to an LQ ball, it's just a fancy way of measuring how sparse you are. If Q is 0, it just means that you're hard sparse. You have a fixed number of non-zero coefficients. If Q is between 0 and 1, it means that your coefficients, you might have many non-zeros, but they decay fast. Right? So what our theorem says is that there'll be a contraction factor. We'll contract times some quantity, this blue quantity, plus times statistical error. Right? So this is what we care about in learning. And so what matters is that we can show you that this term here is small, that it's got to be small so that we're saying we're going quickly up to a radius that's as well as you can expect to estimate from the statistical point of view. Okay, so here's a precise form, but the contraction coefficient is 1 minus the inverse condition number of this matrix. So that matrix could be very badly conditioned. This means the convergence will get slower, and we'll see the theory, the predictions of the theory are consistent. And this prefactor here, what is it? Well, in the case Q equals 0, it's the number of non-zero coefficients times the log of the dimension over n. Right? And so this quantity here is exactly what's known as the minimax rate. There's no algorithm that can estimate a sparse vector to accuracy greater than this based on n measurements. So no algorithm can do anything interesting unless this thing is little o of 1. And when this thing is little o of 1, our algorithm converges very quickly to something that's even smaller than that error. Right? So that's sort of a good kind of guarantee. Right? So let's go back to these pictures. Let me just sort of illustrate what this theorem means in pictures. Right? So in pictures, we have 5,000, 10,000, 20,000. These are sizes of the vector. And we're using a fixed sample size. And the convergence rate is decaying. Right? That's consistent with these pictures, or this theorem, because this theorem, if the sample size is fixed and d grows, this term gets larger. As this gets larger, the contraction factor goes towards 1, and you get slower convergence. Right? So if you trust the theory, then what you would say, well, if I actually increase the sample size as a function of dimension to keep this ratio constant, then the convergence rate should stay constant too. Right? So let's do that experiment. We'll do the same sequence of problems, except this time I readjust the sample size. I essentially give you log d more samples as you go from 5,000, 10,000, 2,000. So roughly speaking, there's just a certain constant factor inflation. This is the same data, just replotted on different axes, and now you see the convergence rates are identical. Right? So there's a sense that the theory is not only sort of qualitatively correct, it's actually in some sense, in this case, quantitatively accurate. What else does the theory predict? Well, it also predicts that if you use matrices that have very bad condition numbers, if you do compressed sensing and you use the identity, then you're going to get a very, very fast rate. But if you start making your matrix have poor conditioning, you'll still get convergence, but the rate should slow down. Right? And that also happens. So here, this is the case of compressed sensing. This is a kind of correlation or dependence parameter. As this increases, convergence slows. If you make it too correlated and use a constant step size, eventually it will fail to converge. But that's, again, consistent with what the theory is saying. Okay, so about 5 minutes?
No more. It's like 7 minutes.
But that lambda max to lambda min in the previous situation was 200, not 5 or 10. So that's max min not in the low dimension space, but in the original full dimensions. Is that correct?
Well, this is a fixed, this is not a random quantity, it's a fixed quantity that you're sampling from. So you can choose that to be whatever you want. If you did compressed sensing, you choose this to be the identity, and then this ratio here is 1, there's an 8 there. Probably the 8 should be not an 8, probably be a 2. But the point is, if you know, many problems that we think about in learning, right, you don't have things that are close to isometry. You have things where there would be a fair bit of dependence between your covariates or your predictors. And this is saying that you're going to pay a price. It's not saying that everything breaks down. It says you'll pay a price because this condition number will get worse. But as long as your sample size is sort of reasonable, you'll still get convergence. So that's sort of the trade-off. We pay a price for poor conditioning, but it's not fatal.
But that's going to be tricky. I mean, if I'm understanding it correctly, that's tricky because if you're in the situation where you had whatever the high dimension was and you're going through the rank 4 or 10 space.
Yes.
And that's not the maximum eigenvalues in the rank 4 space. That's in the original high dimensional case. And you deliberately chose 4 to wash out all those small ones because they were small.
Sorry, where's the 4 that you're talking about?
The example you mentioned a while ago, Netflix was 4, 10, or 5.
Oh, sorry. This is linear regression. If we do Netflix, there's different conditions. So let me show you that. This is for linear regression, sparse vectors. Let's do low-rank matrices. Right, so low-rank matrices, a sort of general model that includes matrix completion as a special case, is that there's some fixed matrices xi, and what you observe are the trace inner products of xi with some low-rank matrix theta star. If you do matrix completion, xi is 0 everywhere except for a 1 in one position. But there are many other models that fall under this. Lots of people have done nice work on multitask learning, identification of autoregressive processes. Many models can be described like this. So let's look at this semi-definite program. We have a quadratic loss with a nuclear norm constraint. Let's study the behavior of the SDP, not for exactly low-rank matrices, because in practice nothing's exactly low-rank. In practice, what happens is you have matrices that have good tail decay, the singular values drop off fast. So if we look at LQ balls with the singular values raised to an exponent q between 0 and 1, it sort of says that you've got a fast drop-off if you belong to one of these balls. And here's the theorem in that case. It says that you should take the sample size to be, let's just think about for q equals 0, you should take the sample size to be rank times dimension, a little oversampling factor of log d, and then what you'll get is there is a contraction factor. The Frobenius norm of your estimate will contract according to this kappa, plus a little bit of error, and that error has the following forms depending on what kind of model you're looking at. Right? So if we look at this, it's saying that the extra slop that we're not optimizing beyond is equal to the rank times the dimension over the sample size. And that's exactly the sort of correct rate. That's again minimax optimal. If you just count degrees of freedom in a rank R matrix that's d by d, it has roughly R times d degrees of freedom. So this again is an optimal rate, and it's actually optimal for all q. Right? So it's the same flavor. We're contracting very fast. We're not actually solving the SDP, but we're solving it to an accuracy that's of the order or smaller than the statistical error. So for a learning person, that's good enough. You might as well stop there anyway. Okay, so we saw some of these plots. This is for matrix regression instead of matrix completion, but you see the same kinds of curves, roughly speaking. That's matrix completion. We looked at that already. Okay, so let me just wrap up. So Yi Ma spoke about matrix decomposition problems, or robust PCA. These are problems where you have a sum of a nuclear norm plus a L1 norm on the matrix elements. If you study these in the noisy setting, right, you don't assume that the matrix is exactly low rank plus sparse. You assume it's approximately low rank plus approximately sparse plus noise. Then it's reasonable to use an estimator that sort of allows for a bit of noisiness. And you can again get sort of similar rates. If you just look at a simple algorithm, let's say that alternates between soft thresholding on the sparse part and singular value thresholding on the low rank part, that will converge again very quickly, geometrically fast, up to essentially the statistical error of the problem. The other problem that I mentioned, holding low, that these kinds of properties still hold for non-convex problems. And so, even though in this case you don't know that there's a unique global optimum, what the theory tells you is that all the optima, global or local, are all within a very small ball. So any sort of reasonable algorithm like projected gradient will go very fast to that ball. And so basically you're solving a non-convex problem. So it's non-convex, but because it's coming from a learning setting, it's not badly non-convex. And so I think that's sort of an interesting direction to explore, to see if other non-convex problems have similar kinds of favorable structure. Okay, so what I talked about is projected gradient. It's a simple algorithm that works for lots of high-dimensional problems. These notions of restricted strong convexity and smoothness are useful. I think it's interesting to be able to solve optimization problems up to statistical precision, but not beyond. There's no need to sort of optimize the noise. I think these notions are interesting because they probably are useful for not just projected gradient, but there's tons of other algorithms, online algorithms, primal dual methods. I think it probably would be possible also to say things for different kinds of algorithms. Here's a few preprints, and thanks very much.
We have time for a few questions.
So to better understand, what is the role of the regularizer? I mean, the regularizer is I mean, when we talk about these decomposable regularizers,
Yes.
What happens as if we deviate from these? I don't have a good sense of what's happening.
Well, what's the goal of the regularizer? I mean, if you're working in a regime where you have fewer samples than ambient dimension, you can't do anything unless you have low-dimensional structure. So all of these regularizers are trying to enforce some kind of low-dimensional structure. Right? So nuclear norm is trying to say that you're either low rank or you're well approximated by low rank. And this kind of assumption is one way of formalizing it. Right? These are matrices that are very nicely approximated by low rank matrices. Right? So from the learning point of view, when you estimate, you'd like to estimate in such a way that you're enforcing that low-dimensional structure. That's the only way you have hope to say anything.
What is the role of the regularizer in getting these results? I mean, not the goal of it.
Okay, sorry. So the role is exactly in this picture here that I began with, right? So in a high-dimensional problem, your loss function always looks like this, right? It's always nicely curved in some directions and very bad, completely flat in others. If you ever go in a flat direction, you can't say anything. There's no way you get linear convergence. So the whole point of the regularizer, either for statistics or for optimization, is to show that the error, either the statistical error or the optimization error, you always want it lying in curved directions. And when you have a decomposable regularizer, whether it's L1 or nuclear norm, what you prove is that it never goes to the bad space. And that's why the interaction between loss and regularizer is powerful.
Your observation about non-convex problem is not going to hold for all non-convex learning problems, obviously. So do you have an intuition when it's going to work?
That's a very good question. No, in general, because this is fairly recent work. So for non-convex problems, the intuition is that non-convex problems are sort of like this, except in this direction they're not flat. They have saddles. They start going down again. But again, if you can construct a regularizer that interacts with the loss so that you don't go in the downward part of the saddle, then it's as if you are again in a kind of convex problem. So Pohling's work exploits a lot of structure. She looks at missing data and she constructs a particular estimator that's non-convex. We don't know how general it is. I think it would be interesting to think if you look at EM algorithms for other problems with regularization, can you sometimes show that they're, even though they're non-convex, they're not badly so? But the answer is I don't know.
But even this condition that all the local and global solutions are pretty close to each other is pretty strong. Is it known what conditions suffice for that?
Well, essentially,
from your perspective, as soon as you have that, you're done.
Yeah, so something like a strong convexity, you don't actually need something quite as strong as this. This implies that all local and global solutions are within some radius that depends on the size of this and the size of this and the relation between these two norms. So you're right. So the name of the game is sort of identifying that and showing that this kind of condition holds for different problems. But yeah, I don't really know. These are interesting questions.
Alright, so maybe last two questions, maybe you in the back.
Okay, so matrix completion forms that you were discussing, are you assuming ignorable missing data patterns or not ignorable missing data patterns?
I'm assuming sort of completely missing at random, as you miss sample entries. I guess there's a poster here that's talking about more general sampling, which I agree is interesting, because in practice, if you watch one movie, you're more likely to watch other movies of a related type. So that's interesting. All the results I put are kind of under the naive. We allow for weighted sampling, but it's IID, it's not dependent sampling. So.
And it's missing completely random, not even missing at
I always forget what's the distinction. It's completely at random in this case, yes.
So in each of the problems you mentioned, the goal is sort of to minimize the error between predicted parameters and the true parameters.
Yes.
How does the problem change when the goal is instead to infer the support of the true set of parameters?
So that's an interesting question. Right, so this is very much tailored towards these kinds of results in terms of Frobenius or L2. So you're asking if I had a sparse vector, or if I had a low-rank matrix, do I get the support? There you need slightly different conditions that are somewhat stronger than this. You need these kinds of mutual incoherence or irrepresentability conditions. I guess it would be interesting to also think about theory for optimization in those cases. In some cases you can use it because if you can show that your algorithm stays at a small support at all iterations, then somehow you're done. Because the problem will be strongly convex when you have a bounded support. But part of the challenge here is that this is a global result. This holds from iteration 0. So it's not just using a support recovery kind of analysis. It's different.
All right, let's thank the speaker.